Hi, everyone. Welcome. Thanks for joining us. My name is Dr. Katie Bateman. I am a professional learning and research manager with the Museum of Science Boston and their PK-12 division, which means that I work with youth engineering solutions, and engineering is elementary. And because of my job, I spend a lot of time in classrooms. I spend a lot of time working with teachers. So I get to go into classrooms and see how this is working with students in reality, right? I'm not there to scaffold or to teach it for them. I'm just there to hang out, videotape, watch, and we're going to see video from a number of those contexts here tonight as we talk about engineering in the environment. And the key piece here is, designing for a sustainable future. And so we'll get going here. Just to give everybody sort of an introduction, we're gonna think a little bit together today about how environmentalism and engineering can work together. With our agenda, we'll start with what even is an environmental engineer? What does that mean? And the way that we're going to do that is we're going to take a little history lesson on where environmental engineering originated. And then we'll look at what resources are available to support this at the PK-12 level. And we'll have space for questions. And a reminder again, the chat function is working. You're all using it. That's lovely. You can raise your digital hand to ask questions out loud. Please feel free to interrupt me. We are happy to have this be more of a conversation than me talking at people. So if questions arise and you want to ask them at that time, please feel free to do so. All right, so what do environmental engineers do? And an environmental engineer, if this is new to you, or you're kind of like curious, don't know what they actually do, they can help us tackle a lot of pressing problems in our current world. Their job is to innovate technology to protect and improve life on Earth. So notice we didn't just say people, right? Life on Earth as it exists. So environmental engineers can share a lot of characteristics with other types of engineers too. Environmental engineers might think about planning cities to cool urban heat islands, or better insulate a house against growing heat or growing cold. Or we've seen a lot of hurricanes lately, right? How do we make things more resistant to wind and water? They might think about better ways to grow food or get rid of waste. And a lot of these problems are not new. In fact, environmental engineers have been around for a really long time. So here we see one that I think is familiar to most people, right? Are the aqueducts used by the ancient Greek and Roman people. And they were there to transport water over miles using gravity. And so we see at the top here, the Roman aqueduct and how we had these bridges that used gravity to figure out how to get water from the reservoirs into the cities where they didn't have as much access to water. We know how important clean, fresh water is to survival. And so finding a way to get that there really was this idea of environmental engineering. And we're still using a lot of this same technology today. We see the modern aqueduct picture on the bottom, where it's kind of running underground now and it's being treated. So there's that extra environmental engineering. But pictured here on the right, we see, and I'm going to butcher the accent here, I apologize, the Aqua Virgin, built in 19 BC. It's been restored a bunch of times, but it is still a functioning aqueduct. It still does its job. And so these technologies help us bring water to communities. I'm going the wrong direction. Let's try that again. We can even track the movements of people when their engineering designs failed to support them in a changing climate. So we see data visualizations here that show the change in population over time to the Harappan civilizations or the modern day Middle East. And so people moved to locations with more water for farming than they previously had in their relatively industrialized cities at the time. as climate change occurred and summer monsoons weren't bringing nearly the amount of water that they were used to, that they relied on for survival, for crops, for drinking. And so as our climate is changing even more rapidly, and we have a global population that lacks room for the increasing number of climate refugees worldwide, new environmental engineers will need to be created to address these problems. So let's take a look here. There we go. Come on. Another ancient environmental engineering design challenge was dealing with the inverse problem of not enough water that we saw the Greeks and the Harappans deal with, but when you have too much flooding from climate change. And so the images we see here are renderings of the work studying the Pengleng Tai people living in the Western plains of China around 5000 BCE. And so they developed a complex series of drainage pipes, ditches, and most importantly, they worked as a community to respond to the emerging crises. Collaboration is an ancient practice of engineers. It's not something new that we're asking to do. And so one of my favorites is thinking about keeping people safe from disease. This also falls under environmental engineering. And so interestingly, this is a sketch of Mesopotamian sewer systems, and they protected the water quality and ultimately the health of that community. So toilets and sewers, yes, are part of environmental engineering as they protect the health of our water and thus the life on Earth who rely on it. Sewers and sewage treatment continue to be environmental engineering challenges. As we reach more modern times, early environmental engineers designed the sewer systems in London. Although the impetus for British politicians to fund this work was the odors wafting into the Houses of Parliament from the Thames in the record hot summer of 1858, which they called the Great Stink. The sewer engineering was actually a cause for the steep decline in cholera cases that were causing an absolute pandemic in the 19th century. And like our Roman aqueducts, this sewer system is still functioning in London today. And we can look at more modern challenges, right? When we start to think about environmentalism, here's where we really start to kick it off. The 1960s and the publication of Rachel Carson's Silent Spring brought attention to the impacts of things like DDT pollution from companies like General Electric dumping manufacturing waste into water systems like the Hudson River. And so in addition to changing laws to prevent this, environmental engineers had to develop solutions to this problem, including dredging, the effects of which are seen on the right side of your screen, capping of the sediments, and more biological engineering ideas, such as adding oysters back into these water systems to help filter the water. And so a big question becomes, why do we need to develop environmental engineers in pre-K-8, in pre-K-12? Because we need a new generation of creative problem solvers who can think about solutions to challenges. And some of those haven't even emerged as challenges yet. We are getting our students ready to address problems that we can't even foresee. And so not 1929, let's try that again. In 2019, the National Science Foundation identified 5 pressing challenges for 21st century environmental engineering. They were sustainably supply food, water, and energy, design a future without pollution and waste, curb climate change and adapt to its impacts, create efficient, healthy, resilient cities, and foster informed decisions and action. These challenges are going to require these engineers to be creative, to be innovative, to collaborate in interdisciplinary teams, and have the ability to anticipate rather than react to problems. And so again, we come back to this. How do we prepare students to address these problems and the problems that have yet to arise? There we go. So here at YES, we know that to have future professional engineers who are creative problem solvers, we need to start them young and we need to make engineering accessible to everyone. Our resources are designed to follow our equity-oriented framework, seen here. And we're going to take a look at how this supports the development of future environmental engineers as we take a look at some of the resources that YES has for you to be able to do environmental engineering with the students that you work with. And so the first of these is socially engaged engineers. We need students to see that engineering impacts our society, our world, and so we designed curricula with this socially engaged engineering in mind. And we've distilled 3 design principles related to that. We want students to situate the problem in a societal context, consider the impact of the problem on different individuals, groups, or systems, and think critically about the impacts of engineered solutions. There's many ways students can form meaningful connections between their lives, communities, cultures, and society, and engineering. Stories are one powerful tool for situating a problem in a larger context and understanding its importance. For example, in engineering plastic filters, students learn about the problem of plastic pollution in Mobile Bay, Alabama, through a graphic novel format and various investigations before designing a solution to the problem by making a plastic filter in Mobile Bay. So here we see our comic right here in the middle, where the students are hearing from different community members and different stakeholders who have different needs that need to be considered throughout this. Come on. We don't expect that students will inherently know how to do these things. We scaffold them at different ages to be able to think critically and develop skills over time to be socially engaged engineers. We designed for a progression here in this curriculum. So keeping with this look at plastic filters, engineering plastic filters, one investigation asked students to consider the implications of plastics, which are a technology, have on the local environment. They see that in some ways, plastic is a more effective choice, although there are consequences on the local and global environment. So for example, students think about what materials are really good for making a ketchup bottle. Is it glass? Is it plastic? What do we want to wrap a sandwich with? Do we put it in a plastic bag? Can we wrap it in paper or tin foil? What's going to be most effective? And why are we making choices about these different materials? And why is it sometimes plastic that's the option? We also ask students to think about how the solution can impact different groups of people. So we're going to listen in now as students from a 5th grade classroom in Pennsylvania consider the impact of the pollution problem on the different stakeholders in the community.
I would say this would go all the way down here. We know this.
That's the most.
Yeah, this is the very top.
And then it's
Fishers, because they depend on fish to get money. Office workers, they don't even interact with fish.
boaters, they don't.
Actually, yes, they do. Because if there's too much pollution in the water, the boat can't sail.
We hear these students developing their ability to consider different needs and use that information in their designed solution. Much like the engineers who needed to develop solutions to New York's DDT problem, there's no perfect solution here. One group is likely to have more or less complete resolutions to the problem. Working through the trade-offs is important for these students.
I would say
Engineering practices are woven into every lesson in the YES units. We just heard students communicating effectively and considering a problem in context. But each of the 16 practices you see here have the capacity to build future environmental engineers. So let's take a look at an example from middle school this time. I'll let one of our teachers describe this middle school unit, engineering medicine coolers.
The engineering medicine coolers unit teaches students about the real-world problem of medications losing their efficacy when they get too hot, so they will get damaged. Students are given that problem, and their workaround for that is developing a medicine cooler to keep these medications at a cool temperature for a extended period of time. They did this through starting out with a cardboard box and taking different insulating materials and lining their box with that. They experimented with potassium chloride to use that as a cooling solution and tested their coolers under a heat lamp to see how long it could keep the inside cool.
There are many practices students engage in throughout the unit, such as exploring the properties of sodium chloride and how it reacts with water to cool various degrees. They use math and science knowledge as they explore these properties of insulators and think about how to use them in designing their solutions. The middle school units also engage students in computer science, thinking about algorithms and how the data put into the algorithms determines the outcome of a data visualization of heat waves, which we see in the bottom right-hand corner, further considering the problem in the context of environmental concerns. It's often the case that we hear students engage with multiple practices at the same time. Here, as students negotiate a design for their medicine cooler, listen for different practices you're hearing or seeing as they happen and share them in the chat. So this is that I said, we're going to get a little interactive tonight. So as you hear these different practices, share those in the chat with us.
So let's go ahead and take a few minutes to work with your groups and talk about what you think might be the best route to take for your coolers and what materials you want to use and how much those are going to cost.
We have a 5x5 box, and that's $125. And then we have a cardboard, but and what I put it on all 6 sides, and that was $3. And then I times it by 2. So
for 2 layers?
Yeah, for 2 layers. That's $6. And then I put 10 grams of potassium, and that was 50 cents. So I did that, and it's $7.75. So that's lower than $9.
So you should probably make it.
No, not make it, but it's under $9. So we don't need to add any more. Unless you, like,
We could
you
just
can't really
add
add
another
anything
10
else.
grams.
You can't. It said the max was 10 grams. So we're at $7.75.
Yep. My apologies. I don't know what's happening here. I'm trying to keep up with the chat and
So let's go.
7 sides.
where were we? Backing it up here. All right.
We don't need to add
out there.
any more.
Sorry about that.
Unless you, like,
We could
you
just
can't really
add
add
another
anything
10
else.
grams.
You can't. It said the max was 10 grams. So we're at $7.75 right now. And I think that's because I tried the felt, and the felt was too expensive.
And so can we add 2 different insulations?
Absolutely.
Okay.
Oh, we could.
We can
Yeah.
add aluminum foil on the
Yeah,
outside.
you can do.
Oh,
that is something
okay.
else. Yeah, you can add materials to the
So
outside.
you
of
want
the
to
box
put a
and-
layer of aluminum foil?
Yeah.
What's up?
Some styrofoam.
No, the aluminum foil can reflect the light.
that your group wants to make.
On the outside of
Yeah,
the box?
on the outside.
So how much are we at?
So if we plus 1.5,
Probably $8.
that is $8 or
No, I think that would be
$9. Oh, we're over.
You can
Wait.
replace one of the cardboard
on,
layers with a
I think it's like
cheaper.
9.20 or something.
10.25.
You can there's nothing else cheaper than cardboard.
Yes, there is aluminum foil.
Yeah,
Yeah,
besides
no,
that.
we're at 8.75.
Okay. So we
And it
have just enough.
Okay.
But then the cold pack is 60 cents.
I forgot. So then we can't do aluminum foil on the outside,
Or we have to make the
or we
box
can,
smaller.
or we can, or we
Remove
can
the layer.
decrease the potassium.
So Thank you all for sharing so many ideas. There's so many things in there. We picked up right away on this idea of they're exploring the properties and uses of the different materials, right? What's going to act as a good insulator? They're communicating effectively. This is a process. The funny part of this is that when these students were interviewed at the end of this unit, they told me about what a struggle it was to cooperatively work in this team together. And we see them having such really good communication with one another. But that took time, it took practice, it took some scaffolding from their teacher to get them there. We absolutely hear them applying their math as they're calculating this budget, practicing real world math skills they are going to be able to use in their everyday life. We see them using that, yes, somebody said, making evidence-based decisions, right? They're really thinking about the outcomes here, and balancing the criteria and constraints. They have a budget, but they also have a goal. They need to keep as much medicine as cool as they can for the longest period of time. But they can't do all of those things at once. They have to balance those trade-offs. And that means thinking about those multiple solutions to the problem. There isn't one way to do this, but we've given them some ethical things to really reconcile with here. Who's going to be helped? Do they help somebody who needs a larger amount of medicine? Do they help somebody who needs the coolest medicine? Do they help people who need the cheapest solution possible, right? So they really have to reconcile this. And it's things that we see environmentals having to do all the time as they think about their solutions. And yes, and I agree with Lynette, they're acting as engineers. They're identifying as engineers, and they're thinking about this as a real problem that's genuine, that is authentic, that is something that they are seeing as something that needs to be solved. Does anybody have any questions before I move past our practices here? All right. Remember, you can interrupt me at any time. I'm happy to pause and answer questions about anything we are seeing.
So let's go.
So getting creative and knowledgeable groups of environmental engineers in the future means broadening participation in engineering to many different kinds of people from different communities, cultures, and backgrounds. Here, I do see a question. Are these engineering practices that are identified in the next generation science standards? Lynette, remind me of that. I'm going to come back because that's a longer answer of a question. I'm going to come back to that one because we can talk about the alignment with the NGSS totally once we get to the environmental stuff, and then we can talk about that alignment because that's a tricky question. That's a longer than a 2-second answer. So we want to make sure that we have students from all different kinds of backgrounds. That also means having pre-K-8 engineering that is inclusive and allows for the removal of barriers that often prevent some groups from fully participating in STEM. If we've always done things the way we've always done them, then we're always going to get the same results that we've always got. We need to have new ideas happening, which means bringing in new people. And asset-based pedagogies can help leverage students' existing capacities rather than identify their limits. In a slick solution, cleaning an oil spill, students are scaffolded in their exploration of pollutants and the materials that may aid them in designing a solution to remove oil from water. Vocabulary cards are introduced in context as students become familiar with the term. They're not pre-introduced. There's not a preset list for them to memorize. We give them something to understand first and then label it. Like environmental engineers, pollutants, or absorption. Those are all words they would learn within the context of this unit. Material sheets give a visual guide to become familiar with the tools and resources they can use in their design or in their investigation. The engineering notebook, which we see in the center there, makes sure that all students can engage with materials like the Imagine page you see here, where students can circle the materials they want to use, checking against the photographs in the materials sheet that you see just to the left of it. So let's listen in again on a group of students testing materials during this unit before they get to their design.
3, 2, 1. It's all black. Oh no, I know something. I know something. I know something. What? Like that. It's red. No, this time me. Whoa. There's almost no oil.
So we see here evidence of other design pieces. Students are engaged in practices around a real-world context. But now we can see all of these students are working together to do it. The hands-on nature has them engaged and thinking, trying different things, and they're able to draw on their real-world experiences in these contexts too. What they already knew about what might soak up oil or something similar can be tried out in their small groups, but they can figure and try things out. And finally, key to this is the development of an engineering identity. We want students to see themselves as capable of engineering. Otherwise, how will we have engineers in the future? Listen to how this teacher sets her students up to see themselves as future engineers.
Who can be an engineer?
Anyone.
Anyone, okay? And I hope that everybody realizes that, all right?
Yeah. And children.
Even children. So not just adults, but even children. Now, of course, if you're an engineer as an adult, guess what?
You know more.
Well, you will, but you also get paid to do. Because you can actually do it as a job. You can be an engineer as a career. You can go to college, learn more about the field, and then eventually you can spend every single day, for example, being a materials engineer, working with a bunch of materials, figuring out how they go together, making new materials from existing materials, okay? It is a wealth of opportunities for people who are interested in engineering.
And so we hear these students understanding that they didn't know that this was something that they could do. They've enjoyed this activity that they've been doing. And now they're realizing I can be an engineer. I can go have this career. I can solve these kinds of problems that are important to me, that are important to my community, and I can get paid for it. And let's be honest, can get paid pretty well to do these things. And so there's other resources too that we have. Many of the YES units connect with environmental concerns in each of our curricular areas. In YES Elementary, students can design hand pollinators to make sure we have enough pollinated flowers to turn into pumpkins for food, or this time of year, for jack-o'-lanterns, for pumpkin pie, whatever the case may be. In rescue shuttles, a YES enrichment unit, students help first responders reach victims of flooding. Another middle school unit introduces students to the problems of waste from discarded shoes and the need to consider the trade-offs between environmentally friendly materials, cost, and the safety of the slipper, as well as the cost of human labor to create this slipper. All of these units are available on our website for you to use in your classroom or program, and more of them are joining soon. At the Museum of Science Boston, we're celebrating the Year of the Earthshot, helping people explore ways that humans can live sustainably. Exhibits, speakers, events, and online resources at mos.org/earthshot, at the bottom of the screen, can further support you as you think about how to fold environmental engineering into students' experience. Whoops, nope, wrong direction. Into students' experiences and create a future generation of problem solvers. No, that was a YouTube video previously. Well, if you go to mos.org/earthshot, you can see that video there. I don't know why it's refusing to play for me at the moment. My apologies. But that will tell you a little bit more about Earthshot and the initiatives at the museum to really think about environmentalism, environmental engineering in our cases, and the things that are available. For instance, later this week, they're having the Youth Climate Summit, as in tomorrow is later this week, it's Thursday. They're having a youth climate summit. There are speakers, there are exhibits. So there's lots of things for people to check out. Some of them also digital for all of our friends who are not coming in from the Boston area that you can access and use with your students or just for your own learning.